Okay, so this is 8.4, lecture number 2. Who knows how many it's going to take us to get through here. We are now on slide 13 of 121. So, like I said, I'm going to break this up a little bit. Okay, so let's see how we did answering that question or thinking about that question. What aqueous species? All right. So because of that, the way it was worded here, some of you might have had H2O as one of your choices. That would be wrong because they asked for aqueous species. So this reaction, because it's strong, is very, very driven toward the right side. Like I said, that OH is going to rip those hydrogens away. So because of that, this is going to be one of the highest concentrations. Okay? Now, this isn't one of the other ones, and neither is this one. Okay? So neither one of these, they're both in a 1-to-1 molar ratio, and most of them reacted to go over there. So this guy's dead first. So here was the trick to the question. The other aqueous species is potassium, the spectator. Did you forget about the spectators? The fans are important. Don't forget about them. They still are there. They just don't get to play in the game. All right? So K plus having a 1 molar concentration will be very similar to NO2, which is going to be certainly approaching that as well because you're driving everything to the right. So there are your two highest concentrations. So a little bit of a trick question there. All right, so now, given this reaction right here, okay, we have a triprotic acid. And remember, we just finished our last lecture. Now, it's certainly okay if you let the problem slide a little bit, but you don't want to... Oh, I'm getting a notice that my battery is running low. Oh, that's because I plugged my phone cord into this cord. All right, so let's fix that and charge my computer instead of... There we go. I fixed it. The battery has been will now be being charged, so I won't get cut off. All right. So you're like, hey, if you're going to have these troubles like this, these technical difficulties, we're never going to get done with these 121 slides. The semester's ticking. Let's get going. All right. So triprotic, H3PO4. You just finished learning that it'll take one hydrogen off at a time. So you know that one of those hydrogens is going to get ripped off by that strong NaOH, which they're in the same concentration. So give this a shot. Hit the pause and see if you can write the correct net ionic equation for this weak acid strong base reaction. Pause. Welcome back. Let's see how you did. First of all, you're going to write this as aqueous, and you're only going to write the OH minus. Did some of you accidentally put the Na in there? Bad. AP no like when you do that. Spectators, stay up in the stands. If we're going to talk about their concentration with that question, we'll bring them back. But do not put it in the reaction. Okay? So, when it does that, you of course are going to get water because the OH takes that one hydrogen and it becomes H2PO4. And remember, it just takes the proton. That's all it's taking. So it leaves the electron there that was in the bond, one of these covalent bonds with phosphoric acid, and so that electron's still there. So the H plus is gone, and you got that minus. So, and again, the charges on both sides will equal out. Okay? So then you're going to answer the question, identify the aqueous species. I'll bet you a lot more of you are going to get it right this time. You got it. It's H2PO4 and Na+. Will have the highest concentrations. Now, this is going to change ever so slightly. We're going to do this same problem, and when you look at it, you go, hey, that's the same thing. Nothing, all those letters are the same. It just changed from X2 to X3. Anything else change? Oh, there we go. Okay. It changed to 2.0 molar. Ah, ha, ha, ha. That is going to make this fun. All right. So now you got two bullies, each wanting a hydrogen. So the first bully that comes in contact is taking the first hydrogen. The next bully is going to take the second hydrogen. That will give you two water molecules. When you do that, and when you remove two hydrogens, then you end up with HPO4 with a -2 charge, because you have ripped two of them off. And that 2 with that minus, the charge is still balanced. And the two OHs will do that. Now identify the species that have the highest concentrations. Going to be the same thing, the HPO4 -2 and A, and the Na is going to be in pretty good shape here with 2 molar concentration, and that's a safe bet. That one has a very high concentration. So that's one of the kind of problems that you'll see. All right. Now, here we have a scenario where we've got 55 milliliters of a certain concentration of a strong base with 55 milliliters of another different concentration of a weak acid. And again, we're going to assume the volumes are additive. They don't always say that in these problems. And then we want to find the pH. All right. So this one's actually has some pretty interesting steps. The first thing you have to do is you got to do a limiting reactant problem. Now remember, that's in this case it's going to be a volume to, we'll just stop at moles. They'll stop at moles, and then you can see which one's going to be the limiting reactant. So you start off with this volume. And take time to get the net ionic equation in there, which is HF plus the OH gives you F minus and water. Okay, so that's a pretty straightforward reaction right there. When we're looking at this, you've got the 0.55 liters of the NaOH. So whenever you're doing a stoichiometry problem, it's always nice to say the unit and the substance, because we're going to change that in the middle here in your mole to mole conversion using the coefficients and balanced chemical equation. There's 2.5 moles per 1 liter for the NaOH, and it's really the OH that we're talking about in this. So it's 2.5 molar OH. So that works out pretty nicely for us. All right, now 1 mole of F minus ion per 1 mole, that's just the coefficients in the balanced chemical equation, giving you, in theory, 0.14 moles of the fluoride ion. Now, if you started with the same thing of HF, then this is your conversion, because it's 2 moles per liter, and the coefficients in the balanced chemical equation, 1 to 1. Okay? As the reaction proceeds, they will be in a 1 to 1 ratio. Okay? So, limiting reactant problem, all you got to do is find the one that's the smallest. and that is the one that will limit and determine the amount of substance that we have. Okay? So, if you were asking the question, what is the limiting reactant, which they said for step 1, it would be hydrogen fluoride is the limiting reactant. And the pH can be found from the moles of excess OH in the solution. Okay? So we now know that there's going to be excess OH. All right? So there are going to be a bunch of bullies around with no hydrogens to steal because they're in excess. Okay? So that's what that tells us. It also tells us that, it's going to be basic in concentration. Okay? So, find the OH in the final solution. Well, in order to do that, you kind of have to retrace the steps that we just did, but with a different purpose. Now, this is missing the mole-to-mole conversion, but I really think it's important that you write this out. I mean, you could have looked back and you go, oh, since this was 1-to-1, that's going to be the answer. Well, yeah, you're right. But just show that you know what you're doing and that this is a different problem here. Okay? So this is, I'm trying to find out the moles of OH. So now I got it. That was not what I got for the answer here. That was moles of F minus. And just because the numbers are the same doesn't mean it's the same thing. This has one fewer step. So when you're doing the HF, a 2 molar concentration would give you 0.11 moles of HF. Now, this step, I think you can go personally right to this step, finding the OH, because when you do this, you just take the big one minus the small one, and you have OH remaining from the final solution. The previous slide, I think, was just showing that conceptually it is a limiting reactant, and you're going to have one thing in excess. So this works out real nice. You just subtract them, and just the big one minus the small one, and then you know that you have excess OH when you are doing this. And volumes, they said, are additive, so just add them up, put that over there, and that's 1 sig fig. That's what they gave you. When you do the math on there, 2 places to the right, you got to stick with the 1 sig fig. So it's 0.3 molar. And that is the OH concentration. POH equals the negative log of the 0.3. POH equals 0.5. They actually asked for the pH, so you're going to jump up here and say the pH is equal to 13.5. Okay? So another really good example problem of how you go through these. I'm going to let you kind of focus on, getting caught up. Work on those 8.3 problems that we assigned yesterday. There's lots of those. And then just kind of start taking a look at these problems. I'm going to let you know a little bit more about that. So we're getting caught up with the concepts. Make sure that you're getting caught up with the work. And so we'll just stop with the 2 lectures today. And we will forge on with that tomorrow on Friday, when we have all kinds of energy to attack the rest of this big, giant topic that is about dealing with weak acids and strong bases. Because you can see it does get kind of interesting when you're crunching all these different steps. You got a 4-step problem here. Okay? All right. So, anyway, go ahead and start these problems if you want, but use work time for catch-up. Bye.